everyone. Thank you so much for joining us. My name is Aurora Elmore, and I'm the Cooperative Institute Manager for NOAA's Ocean Exploration. As such, I have the very, very wonderful opportunity to work with the Ocean Exploration Cooperative Institute. OECI, as we call it, is made up of partners at the University of Rhode Island, University of Southern Mississippi, Woods Hole Oceanographic Institute, the nonprofit Ocean Exploration Trust, and the University of New Hampshire. Today, our speaker will be Dr. Larry Mayer from University of New Hampshire. He is the director of CCOM. He's worked with NOAA for quite a few years. I'll not say the number. He's been, a wonderful collaborator with us through OECI and, of course, to Coast Survey as well. So we're really pleased today to have him discuss something that OECI has been working on for the past few years, which is getting lots of vehicles in the water to rapidly increase our pace of ocean exploration. So Larry, thank you so much for joining us today. It's quite an honor to be able to introduce you, and I will hand it over to you for the rest of the presentation. As Katie said, please feel free to put your questions in the chat, and we will have some time at the end of Larry's presentation to try to get through those. Thanks so much, everyone.
Well, thank you very much, Aurora. It's a pleasure for me to be here. And what I'm going to try to do is, as Aurora says, talk a little about our activities in the context of the Ocean Exploration Cooperative Institute. So let me take a moment to just describe that. Aurora gave a little description, but the Cooperative Institute is really a collaboration between 5 institutions and ocean exploration. And it's been a new experience for me. It's the first cooperative institute I've ever been involved in. It's been a learning experience, but it's been an excellent one. I think it's really evolved, and I'll talk about that in a moment too. But the mission really is to explore the USEEZ, to develop new technologies, and to engage and train a diverse blue economy workforce. And I think we're really making progress on all of those. And Aurora explained the partners: the University of Rhode Island, the Ocean Exploration Trust, Woods Hole, University of Southern Mississippi, and our institution, the University of New Hampshire, particularly the Center for Coastal and Ocean Mapping. We have a number of tasks in there. Whoops, I went too fast to a slide. I'll get this eventually. Let me try it this way. There we go. I think I can do it that way better. Just hold on a second as I get my arrows in the right direction. There we go. Okay, we have a number of tasks, and the area that we've been focusing on at UNH has really been that of the technology development. And there are several aspects to it, but the one I'm going to focus on today is what Aurora mentioned, and that's what we call expanding the footprint of ocean exploration. Historically, we've gone out on a large ship, and when we go on ocean exploration missions, we typically will use that ship as a mapping platform. Sometimes we'll have a remotely operated vehicle on there, and we'll stop the mapping to launch the remotely operated vehicle. We can have an autonomous underwater vehicle on board. We'll stop the ship's activities to launch the autonomous vehicle. We'll use the ship to kind of coordinate the activities of that autonomous vehicle. It tends to be a single vehicle focused operation. And what we were trying to do is see if we can expand that footprint and see if we can really learn how to use multiple vehicles at the same time, or actually create a much more efficient operation. And again, through the partners that we've been working with, particularly for the work I'm going to talk about, Woods Hole, and a vehicle that they have called Mesobot, which is a mid-water vehicle, a very slow-moving vehicle. It's designed to follow plankton in essence, using cameras, and has eDNA samplers. And Woods Hole's NOAA hybrid vehicle, which is an autonomous underwater vehicle that has both a fiber optic cable to allow it to act as an extended ROV, but if that fiber breaks, it can then act as an independent AUV. And then, of course, the Ocean Exploration Trust with its vessel Nautilus and their ROVs, in this case Hercules. And the idea was how we could coordinate the activities of all these vehicles with our contribution, which is a surface autonomous vehicle, something we call the DRIX. And of course, this is all coordinated through the Interspace Center at Rhode Island, extending the communications capabilities, bringing scientists from all over the world, and bringing educators and students in the public, into the action, in essence, through telepresence and what we call teleoperations. I said this has been an evolution. When we first started and looked at the assets of each of the institutions, it was kind of a typical academic, well, what are they doing? What are we doing? But what I've seen evolve over the last 2-3 years is really a remarkable bunch of collaboration, really focused around the Ocean Exploration Office. And they've really pulled us together. And I think we're all gaining from that experience. So what I'll focus on talking about today is our activities at the University of New Hampshire, which revolve around a number of vehicles. I'll focus mostly on the DRIX, but I want to give you a little background about our center and how our interest in autonomous systems has evolved and where we're hopefully going with that too. So the Center for Coastal and Ocean Mapping at the University of New Hampshire is a national center of excellence in ocean mapping. We have quite a large group, over 100 staff and students. And our mandate is to develop innovative approaches to ocean mapping and to train the next generation of ocean mappers. And in doing that, we serve many folks, but for the most part, our main client, so to speak, is NOAA, of course. And as Aurora mentioned, it's historically been the Office of Coast Survey, that part of NOAA that was charged with chart making, with the shallow water hydrography or map making. But that's really expanded over the years. But through our activities with Coast Survey, we were charged early on, probably 6-7 years ago, to start looking at the potential for autonomous or uncrewed, more accurately, because none of these systems are really autonomous yet, uncrewed systems in terms of their ability to serve that mapping mission. And so we started by exploring some small little systems for very shallow water activity. We grew to a 4-meter vessel, something called the Seaworker 4, which has much, certainly in terms of endurance and speed, better capability than the small little vehicles. And we've been doing a lot of work with Sail Drone and their very large platform, the Sail Drone Surveyor. Now that, I won't talk much about that. I won't talk any more about that here, but that could actually be a very interesting subject for a whole nother seminar as we're gaining experience with that vessel too. Our real workhorse became over the years the Seaworker 4. It was really not built for this purpose. It was really built as a target drone. And so its seakeeping capabilities were marginal in a sense in rough seas. It had 4 or 5 knot speed, a reasonable endurance, but we put it through a lot of exercises, working in kind of hazardous areas, very close to the island, around the Channel Islands, doing some work off Point Hope in Alaska, and having supporting the sanctuaries, a shore-based mission in the Great Lakes, Thunder Bay National Marine Sanctuary. It was also used to do the mapping very close around the island in Ballard search for Amelia Earhart around Nicomarora Island. At the same time in our lab, we have a number of things to try to support that activity, and a lot of them are focused on this concept of taking these vehicles, which are now unmanned but not autonomous, and trying to really make them autonomous. And so we're trying to develop software that will basically pay attention to what's on the chart, have navigation that's aided by the chart in an autonomous vehicle, where it's aware of what the features on the chart are. We're looking a lot into machine learning in terms of identifying objects, so we can tell a sailboat or from a seagull as we are trying to avoid objects. But we're also trying to teach the vessels behaviors that are both sensible in terms of avoiding obstacles, but also maintaining their mission. How do you compromise in terms of where you're going to go and maximize the mission that you're sent on? At the same time, we've been doing a lot of work developing what we call a backseat driver, a situational awareness system, we call it CAMP, that will let us see the vehicles, communicate with the vehicles, and collect all kinds of data. And you'll see that that kind of development that we did for other purposes becomes very, very useful as we started to enter into the Ocean Exploration Cooperative Institute, particularly because the software we developed for this backseat driver is based on what's called a robot operating system, ROS. And this is hopefully becoming a standard across many, many vehicles and many platforms. It's certainly a standard across all the vehicles that we're using, and everything we develop is in that ROS environment. We also have a wonderful visualization lab in our center, And we've been using their capabilities to take the kind of information we need for situational awareness. We have these wonderful camera systems on the vessels, in this case a 360-degree 8K camera, but how do we take that 100 megabyte per second of information that it's collecting and transmit it back to us on shore or on a mother vessel? It's a tremendous challenge. So they've been working on ways to compact, to pull out the regions of interest and be able to transmit just critical features through those limited bandwidth transmission paths. And we'll talk a little more about that in a few minutes. And finally, in terms of the background research we're doing, we do a lot in the lab in terms of both VR, virtual reality, and AR, augmented reality, in terms of building those environments. But we're looking at this in terms of using these as the control station for these autonomous vehicles, where we'll gather that situational awareness and have the operator be able to see it in a much more intuitive way. And so I just wanted to give you a feel for the kind of things we've been doing in the lab that support our autonomous system activities. But let's get back to the vehicles again. And as we were exploring, we were working with our Seaworker 4 for a long time, finding its good capabilities and its limitations. And then we were approached by another group to try out a vehicle that was actually purpose-built for mapping. And this is a vehicle called the DRIX. This is, as you can see, a very different hull design. It's a wave-piercing hull, and it has the capability to go at high speed. And if you can see in this image here, the gondola it's raised at this point, actually is lowered 2 meters below the vessel to have the mapping systems installed there, is out of the wave base, out of the RC interface, and really can improve the quality of data even at high speed. And so we got to use this for a couple of weeks in late December of 2018. They loaned us a system. We put it through a bunch of trials, and we were remarkably impressed. Even in very, very rough weather, the vehicle was amazingly stable, and this is kind of a distribution of roll, almost no roll, as we got wind gusts up to 35 knots. So it really, really works well as a wave-piercing hull. And we also put it through its test in terms of mapping, and we got very, very high-quality data. There's uncertainty maps here showing all really acceptable data for hydrographic purposes, with no degradation as we got up to speeds of 12 knots. And that's, again, because of the hull shape and that deep keel. And so we were quite impressed with it. This is, for those of you who know about multi-beam sonars, this is an EM2040. That's a 200 to 400 kilohertz system meant for mapping at water depths. Oh, ideally 200, 300 meters, maximum 500 meters. You get a narrow swath in that depth. And so when it came time to think about a vehicle for the Ocean Exploration Cooperative Institute, from the seakeeping capabilities, from the high speed and the long endurance, this vessel has an endurance of about 7 days at 7 knots, and the fact that it was transportable in a small container, we thought that this might be a great platform for us to start exploring this idea of expanding the footprint, also having a mapping capability. Although at this point, and I'll get to this towards the end, having a mapping capability only to 200, 300 meters was not really right up OECI's alley. OECI interested in deeper water exploration. But I'll talk in a few minutes about how we've tried to expand that depth of that mapping capability. And so we looked into things quite carefully and made the decision that this would be a platform that we'd invest in. And the OECI then purchased what we call DRIX 8. It's the 8th, the one that was made. And we took delivery of that in November 2021 and put it through a bunch of initial sea trials. And that's what we tend to do at UNH. We take these vehicles and really find out what works and what doesn't work. And we work closely with the manufacturers and kind of beat out the problems. And by January, February of 2022, we were ready to start embarking on missions for the Ocean Exploration Cooperative Institute. And that involved the installation of the DRIX itself, the orange vehicle, and its launch and recovery system, something we call the UDS, Universal Deployment System, this large gray thing, on the exploration vessel Nautilus. It meant installing a new crane and going through a whole bunch of operations that none of us had ever done before. And I can't thank the OER and the OECI enough for allowing us to have a 10-day shakedown cruise, that 10 days of practice, going through drills of learning what works and what doesn't work and how to do this and getting everybody familiar with it, paid off in spades. It was a tremendous opportunity to really let us understand how to work a new system on a new vessel. With that under our belt, we then set off in May for our first real mission, which was what we call a technology challenge. And this is the mission that's really the focus of this presentation. This was the mission to see if we could demonstrate collaborative behaviors between multiple vehicles and truly expand the exploration footprint, not be constrained for a single surface ship supporting one operation at a time. And again, the vehicles we had with us were our DRIX, the Hui Mesobot, the Woodsole Nui, and the Nautilus, of course, as the manned research platform. And kind of jumping to one of the conclusions, it was just a tremendous success. We had 8 deployments of the DRIX over that time, and most importantly, 8 recoveries. And we were so confident in our operations, even though this was the first time we were operating offshore. We had even an overnight mission, a 14-hour overnight mission. During that time, we also had 6 separate shallow water mapping missions. You can see each of them in their areas here. But most importantly, and this really was due to the fact that we had that practice on the shakedown cruise, we had very, very smooth and routine. Certainly by the time we were done with that leg, we could launch this entire 5-ton package in less than 5 minutes if we had to. But typically, 5 to 8 minutes, it would be over the side and launched. And you can see it's quite a hefty package there. We also, on that leg, really kind of perfected our recovery. The vehicle has an automatic docking mechanism. You're seeing it here navigate into the UDS, and it's doing that through both radar, LiDAR, and GPS. And so that's a kind of hands-off recovery as it swims in. And each of our 8 launches were recovered through what we call auto docking on that leg. And you see it's not a flat, smooth lake out there at all. We also were confident enough in the course of that leg that we were comfortable having DRIX going off and doing its mapping in the shallow water, and then sending Nautilus off to do its mapping in the deep water, separated by, in this case, no more than about, these 2 sites are 14 kilometers apart, but our maximum separation with full situational awareness was about 20 kilometers. There's something called the marine broadband radio on the DRIX, and we were getting enough bandwidth on that marine broadband radio that we were able to not only have the full situational awareness of where the vehicle was, see it on our control panels and things like that, but also get all the data back transmitted, all the multibeam data, and this is shallow water, high resolution data, transmitted back to us at the end of each line, which allowed us to actually create the end mapping products. By the time the survey was over, we had the final products all collected. We were quite surprised that we were able to do that. And that at this time is limited to the range of that marine broadband radio, about 20 kilometers. I'll talk again at the end of the talk about where we're going next with respect to that. So we got the kind of 2-ship operation kind of under our belt. We were quite happy with that. And now the question was, can we start doing this multiple vehicle activity? Now, the first thing we had to do is kind of teach the vehicles to talk to each other and behave properly. Mesobot, as I said, is a very, very slow moving vehicle. It moves about just a knot and a half, just slowly to follow plankton and image and sample plankton. DRIX likes to go very, very fast. And so how do we get DRIX to follow Mesobot? And so we created a behavior where it just kind of circles around and loops around and loops around. And that worked beautifully. DRIX was able to follow Mesobot. It could communicate with it through a short baseline navigation system. Mesobot has no idea where it is in the world. Mesobot only knows to go to a depth and travel at a depth for a certain amount of time. But with DRIX above it, we were able to track where Mesobot was and get its position and depth. and provide that information to our display systems. And so we would see where the ship is, and we'd see where Mesobot was, have full situational awareness. We were also able to start sending commands to Mesobot. And we can do this all again within about a 20-meter range from the vessel. Now, Mesobot is designed to go and sample plankton, but it has no way of seeing where the plankton is. It has a pre-programmed mission, typically, go to 100 meters or so and sample along that for 10 minutes or something like that. But on the DRIX, we have what's called an EK80, split beam fisheries sonar, a calibrated fisheries sonar, and that lets us see what's in the water column and lets us see midwater targets. So in this display here, you can see the seafloor in red here, and this is a midwater scattering layer, plankton layer of some sort. And we could see that on the mothership sitting on Nautilus, transmitted through the DRIX. It's coming from the DRIX. And we would then command Mesobot and tell Mesobot, well, we know now at 82 meters, there's a layer there. We know what its position is. And we would give Mesobot directions to go left, right, up or down. And we would direct it directly towards that layer. What we hadn't realized when we did this is that we could also see Mesobot very, very clearly from the DRIX as it approached the layer. And so here we're sitting on the Nautilus now, and we're seeing the EK80 data, seafloor, the target plankton layer that DRIX is sitting over, and now we're watching Mesobot as we're directing it to that layer. And then we have no question then when it gets to that layer. And so we can direct it directly to that layer, have no question that it's in that layer, and then say, now turn on the eDNA samplers, and we know that we've sampled in the layer we wanted. And so I call this verified directed sampling. There's no ambiguity about where we sampled or what we sampled. I think this really opens up a whole new world of applications. It also lets us address this question, I think, that many of us had who do any kind of sampling in the water column of avoidance. Are the critters avoiding the vehicle as it comes in? And you see in this case, there seems to be no avoidance at all. But let me show you another example in another area where as Mesobot was coming up into the scattering layer, we see that the scattering layer starts to move up and starts to disperse. And here, we can actually change that. We can tell Mesobot, go follow it, or we can basically choose not to sample. So again, this whole new world of verified and directed sampling, I think, is very, very exciting. We also were able to transmit the CTD data that Mesobot collects as it moves up and down through the water column. So in the real time, we were getting real input on what the water column properties were. So we could see the EK80 data in the context of understanding the salinity, temperature, and pressure differences. We pushed that a little further. Mesobot's a tiny little vehicle. You can see it here when it comes to the surface, often very hard to find. Mesobot on occasion would surface prematurely. NOAA on occasion would surface prematurely. And so, again, through lots of work between the collaborative teams, between Woods Hole and us in terms of exchanging messages, we were able to develop a protocol that should one of the vehicles come up prematurely, the DRIX would run right towards it, go through a search pattern. And we even found that we were able to see even that small target on DRIX radar. And so we had an extra close at hand search tool when these vehicles came up. And certainly from the mothership, it's a lot easier to see where DRIX is than that little yellow target. Okay, so we did the collaboration and coordination between the vessel and Mesobot, and now it was time for NOAA, and we went through basically the same set of exercises. I won't repeat it again. We developed communication protocols between DRIX and NOAA. We had full situational awareness on our displays, so we knew where they were. We were able to, just as we were able to see Mesobot, we were able to see NOAA and get confirmation of its position and depth. And most exciting, and this is what sets it apart, with NOAA, a vehicle working on the bottom, we were able to start transmitting acoustic data that NOAA was collecting, mapping data or imagery data, using Woods Hole's very, very clever data compression approaches, what they call a co-exploration data. And we were able to send through series of compression steps, mapping data through DRIX back to the mothership. So we actually were getting pictures of the higher resolution data from NOAA near the seafloor, and even the imagery transmitted through DRIX back to the mothership without the AUV having to come back, which is really, really quite cool. And so this was all working very nicely, and we decided to really, really put it to the test. And we said, could we put all the vehicles in the water at the same time? And could we be so confident that we could let the Nautilus move away and do something else, which is what we did. We sent DRIX out, and DRIX found a very interesting target, this little pinnacle. And this was it was a hypothetical mission, but we went through all the steps. We said, well, what is that? We'd like to explore it near the seafloor. We'd like to see if there's an expression in the water column of it. Is something happening with the plankton layers there? Are the hydrothermal vents or something coming out of it? So we DRIX found the target, circled over it. We sent DRIX directed the Mesobot to the target area in the midwater. And then NOAA came, and NOAA came out there on its tether, on its fiber optic tether, with DRIX tracking and following it. Again, with full situational awareness, we were able to track the position of all the vehicles, the DRIX and the Nautilus, all at the same time. And then NOAA cut its tether. So it was now a full AUV. That operation kept going with DRIX being the shepherd and the monitor and the relay for all the data. And Nautilus was now free to go off and do its own mapping. And so we were quite happy and quite excited. We were exploring the surface, the midwater, and the seafloor simultaneously, and at the same time, the mothership free to go off and do something on its own. Now, in this case, all limited by the range of that marine broadband radio, about 20 kilometers. And again, in a few minutes, I'll talk about the next step. So I think this was just a wonderfully successful operation. We'll hopefully put this into science application in the coming year and really start planning eDNA sampling programs around features and things like that using these protocols. And just to show you, this was the target as seen by the EM2040 from the surface. This is DRIX map of it. And then when NOAA came down right close to the bottom with its high resolution sonar, its 455 kilohertz sonar, we get the image to look like that. So again, all these exploration, surface, midwater, and seafloor at the same time. Nothing is perfect, of course. We have some constraints. We're still learning. Right now, as I said, the big constraint is that this kind of full situational awareness and data transmission capability is constrained to that range of about 20 kilometers. And again, I'll talk in a few minutes about how we hope to push that to fully over the horizon. We are always going to be constrained by weather, and as I'll show you in a few minutes, DRIX has some real great capabilities with respect to working in rough weather. Once it's in the water, it's the launch and the recovery. That's the big constraint. And of course, you always have to worry about safety considerations. If a vehicle like this does have a failure, you're going to have to put people in the water to try to recover it. And again, because it is autonomous, and we still don't have, because it is uncrewed, excuse me, and we still don't have full autonomy, we always have to worry about just how good our situational awareness and our obstacle avoidance capabilities are. And that's something we're working on all the time, but there's still a lot of work to be done there. Okay, so what I want to do now is transition to the last leg of that we had with DRIX on the Nautilus, part of the OECI season, but this was a collaborative program really between OECI and the Office of Coast Survey. And it was really a test and a demonstration to Coast Surveyors as to whether we could do dual ship operations in a NOAA Coast Survey mode. Could you have a mothership and then a small autonomous vessel operating simultaneously and independently, and again, increasing the efficiency of the entire operation. And in this case, we worked around a very small island in the Hawaiian chain called NOAA. It's an area that NOAA had flown LIDAR, laser measurements for the very shallow water, but they couldn't quite cover the entire area. It just got a little too deep, but that depth is perfect for the sonars that were on the DRIX. And so our goal was to see if we can fill the gaps there in an efficient way and compare the data we'd collect on the mothership to the data collected on the DRIX. The interesting thing about this leg is that the weather was much, much worse than it was on our previous leg. So bad that we did not feel comfortable launching or recovering the DRIX. We were comfortable, if it had been in the water, it would have been fine, but we were not comfortable in those conditions to launch or recover it. And had we been a NOAA survey vessel with manned launches, they never would have launched or recovered the manned launches in that weather either. And so we had to make a decision what we were going to do. And here's where the endurance and the speed of the DRIX really came into play, because we were about 120 miles. This is NOAA out here. We were about 120 miles from Kauai. And what we were able to do, because the DRIX can travel at 10, 12 knots easily, and so can the mothership, is we were able to run back to the lee of the islands here, launch the DRIX in the lee of the island, and then run back and still have enough endurance to survey three days or so before having to do that again. And it turns out the weather calmed down a little. We didn't have to do it again. We were able to launch and recover out there for the rest of the time. And so this showed us a real example of one of the real advantages of a system like this. Had we had a manned launch, we never could have done anything like that. We could have run back here, launched a manned launch, but you couldn't have run the manned launch back there. People would have just been beaten to death, and then they couldn't have spent 3-4 days there. And so another real example of how we can gain efficiencies by having this endurance and this seakeeping ability and speed. And once again, once it's in the water, even in relatively rough seas, sea state 4, sea state 5, it still collects very, very good data. And so even at high speed, we were able to collect hydrographic quality data. And by the end of the day, we were able to fulfill our mission requirements very, very nicely, with 95% of the data meeting or exceeding the NOAA specifications for those water depths. So this was, again, another success, and to me, another wonderful example of inter-NOAA cooperation, of the Office of Coast Survey cooperating with the Office of Ocean Exploration. And I think all of us benefit when that kind of cooperation happens. And this has led now, let me just to wind up the story and to show us where we're going, to the purchase now of another one of these vessels. DRIX 12 now was recently purchased, and here collaboration between the Office of Coast Survey, the mappers, and NOAA Fisheries, because they want to use it in fisheries surveys too. And so this DRIX 12 was delivered again to UNH in August or so, July or August. We again put it through its trials, kind of get beaten up and figure out what works and doesn't work. And when we were finished with that, here's arriving at our area. We have a nice high bay facility that we can work on it in. We had training for NOAA people out there. And when we were finished, it was sent out. Oh, this is what I wanted to mention. Sorry, I forgot about this slide. While we were there, we tried something new. The vehicle was actually operated some of the time while we were in New Hampshire, and the vehicle was in New Hampshire. It was actually operated by operators in France. They can operate it through what we call a Certus satellite system. They get very, very limited situational awareness information in terms of real-time data, but enough that they're comfortable in terms of operating it. So that's a medium ground in terms of this over-horizon capability. I'll talk in a few minutes about where we think the next step in that is going to be. So we tried that out for the first time with DRIX 12 in its operations in New Hampshire. It was then brought to the NOAA vessel Thomas Jefferson, where it was installed, in this case, in a very different way than we operated on the Nautilus. In this case, because the Thomas Jefferson is used to having manned launches, they have davits on board, and so the davits were modified to be able to handle the DRIX, and they worked out protocols to launch and recover from the davit. We just had to build a little adjustment to the davit. And you see the DRIX again, when recovered with the gondola retracted, once it gets in the water, the gondola is extended. They also had to install, as we installed on the Nautilus, what's called a painter boom. It's very important that the DRIX be able to be deployed and recovered not directly next to the vessel. It needs to be kept off the vessel, and to do that, a painter boom had to be installed. It was installed permanently on the Nautilus. Interestingly enough, on the Thomas Jefferson, they couldn't, in the time they had, install a permanent one. So this one was installed, believe it or not, with an electromagnet. So it's a big electromagnet holding it up against the ship, and that worked reasonably well most of the time. Occasionally not, but they'll do it more permanently in the future. And so again, they had their missions really running coast survey-like missions in terms of surveying with the two ships, and they had a number of 36-hour deployments. They stayed within 5 nautical miles of the ship, again allowing that marine broadband radio to allow them full situational awareness, and surveyed consistently 8 to 10 knots. And I guess they were so satisfied that there was an announcement yesterday. I'm in Norfolk at NOAA meetings that by the end of the year they're going to declare this an operational system. So they're quite happy. The next step will be then, and it's happening right now, that the system's going to be deployed on the Oscar Dyson for fisheries work. And so the same vehicle will be applied to a very, very different program. So we've seen it used for hydrographic work. We've seen it used for NOAA's ocean exploration mission, and now for NOAA's fisheries mission. And again, I want to just emphasize what a pleasure this is to me as a taxpayer and as somebody who's worked with NOAA for years, to see that kind of coordination between all the different lines in NOAA. And we all really gain, and NOAA gains, I think, by sharing that information and sharing those experiences and sharing facilities. And it's really, really a wonderful thing to see. So I want to end by just looking at where we're going, coming back to the ocean exploration mission and looking at where we're going. And as I mentioned earlier, the mapping system that's on the DRIX-8, the one that's owned by OECI, is EM 2040. That's a system 200 or 400 kilohertz. And again, will not really map, will map efficiently up to about 300 meters, maximum 500 meters. But the OER mission is deeper than that in many cases. And so what we've done, and this is another risky thing, and that's the wonderful thing about research, is that you can take those risks, is we've worked closely with Kongsberg, the sonar manufacturer, with IX Blue, now called Exhale, the DRIX manufacturer, to see if we, if I keep saying get a round hole in a square peg, or a square peg in a round hole. The EM 712 is a very, very large sonar, both on the array side, but mostly on the electronics end. And what Kongsberg has been able to create is a compact version, not of the arrays. The arrays stay the same size, but the electronics. They've taken a lot of the electronics that would sit on a large ship in several large racks and squeezed them into one small compartment that now actually fits in the gondola, because there's no room in the DRIX for these large electronics. And so that has been built. The gondola is a little larger. It will slow the DRIX down some, but not too much. We think it'll still do 10 knots just fine. It's risky. It has been tested, though. It's been tested in France, in the Mediterranean, and beautiful data in 1,200 meters of water. And the question is, how deep can we go? Here, the deepest water they had was 2 kilometers of water, 2,000 meters of water, and it's still getting a swath that's more than 1 times the water depth. So we have some faith that the system certainly works. It's being shipped right now to Hawaii, and over the next few weeks will be installed on DRIX-8, on the OECI DRIX, and come the start of the season, end of April, early May, we'll be having its first shakedowns, and then hopefully operational missions with it. We're quite excited about that, now adding deep water mapping to the capabilities for OECI. The second aspect of our future activities, and the one that I'm very, very excited about, is really pushing this over the horizon connectivity. We've been able to do amazing things within 20 kilometers or so, but and I showed you that they can operate the DRIX. They get enough situational awareness that they can operate it from France or anywhere in the world. with the Iridium Certus system. But we want to see all the data coming in and really be able to push us to get full situational awareness. And so what we're going to be doing is taking advantage of the new low Earth orbiting satellites, the Starlink system. We've installed the first Starlink antennas on the DRIX, and we'll again be testing that out in this coming season. And hopefully, if that comes to fruition, we should get enough bandwidth, should be equivalent to our marine broadband radio bandwidth, that we will have full situational awareness, full data transmission from anywhere. I don't want to yet say anywhere in the world. I want to say anywhere there's Starlink coverage, but hopefully, not too long, that will be anywhere in the world. And with that, I'd like to stop. I'm tired. You're probably tired of listening to me. I've got a couple of videos I can play if you want to see more. But maybe if we turn now and see if there are questions out there, and maybe while they're queuing up questions or not, I'll play two videos for you. I'll show you one to give you an idea of this auto docking, how the laser system is working, and focusing on two panels that are on the back of the DRIX delivery system or deployment system, and the vehicle will navigate itself in there, again aided by GPS. And then finally, I'll just show you a kind of a pretty highlights video of DRIX in operation. It's like the Baywatch video in slow motion. It looks really beautiful as it cuts through the waves. And let me end there, and again, let me thank the Office of Ocean Exploration for giving us this opportunity, for demonstrating this cooperative behavior between not only the collaborators, but the other parts of NOAA. And, you know, I'm not still 100% convinced that uncrewed systems are the way we're going to go, but I'm getting more and more convinced, and I think they really may be the way of the future. So thank you all for your patience, and I'm happy to answer questions. So this is the UDS, and you see follow those two green dots, which is where it's guiding it. You can see the infrared camera here at the same time. Aurora, do I turn it over to you now? Do I have to do anything?
You can turn it over to me. Thanks so much, Larry. I really appreciate the presentation. It's been really amazing to watch this project grow. I had the opportunity to spend some time with DRIX 8 back in July of last year, and since then it's been out on numerous cruises, and to see it docking itself in the video is just really, really wonderful. I want to echo all of the thanks and cooperation that you noted. You know, it's wonderful for you to be able to present here and to highlight the amazing cooperation that has happened around this project. We've got NOAA Ocean Exploration, NOAA Coast Survey. We've had a lot of folks from other agencies be interested in this project, as well as I see a lot of names from our OECI partners on the call today. So big thanks to all 5 of the OECI partners who've participated in this endeavor. So with that, I want to thank Dr. Larry Mayer again for that wonderful talk. It is just so inspiring to see all the groups working together. I want to thank all of the OECI partners, University of New Hampshire, which hosts Larry, but of course also University of Rhode Island, University of Southern Mississippi, Woods Hole Oceanographic Institution, and Ocean Exploration Trust are all wonderful partners working together to solve these big ocean problems. Thanks so much for joining us for this NOAA Science Seminar, and we hope you'll join us again soon to learn more about OECI and DRIX and lots of other really cool vehicles that Larry's mentioned. Thanks so much, everyone.
Thank you all.